A-Level Physics Lesson 52, Impact Forces. When two bodies collide, the duration of that collision is not zero. It's not an instantaneous collision. There's always going to be a duration of the collision and an interval of time over which the two bodies that are colliding are in contact with each other. So, for example, if I have a ball being hit with a bat, the ball will deform, the bat will deform, and as the two bodies are in contact with each other and that deformation happens, there is the transfer of momentum from the bat to the ball. And then when they're no longer in contact, that transfer of momentum stops. And the total amount of momentum that has transferred, we call the impulse. Let's draw a quick sketch of a bat. That's a bat, isn't it? There we are, rounder's bat or something. And here is my ball, which is being deformed. Now, if we look at the ball, the initial velocity of the ball may well be in this direction. And the final velocity of the ball may well be in the right-hand direction, and maybe even be bigger than the initial velocity in terms of magnitude. So that's fine. The change in velocity is therefore equal to the final velocity minus the initial velocity, and minus means you turn the vector around and add it on. So the change in velocity is going to be equal to, that's my v, and that's my negative u added together. So that is going to be my change in velocity. The ball, so I'm going to say ball deforms, and so there is a duration of collision. I'm reluctant to call it a time, and I've already talked about why that is in a previous lesson, so I don't want to go into that again now. Okay, so what? Well, so that force that the ball is experiencing is going to depend on how much the ball is deformed. And we cover this in the materials topic, which if you've done it already, because you're doing it in a slightly different order to this, great. If you haven't, then it's a reminder of GCSE. Take the simplest example, let's call it Hooke's law. If I take a spring and I stretch it, the force that that spring pulls back with is proportional to the extension of the spring. So the more deformed the spring is, as long as it's elastic deformation, the more deformed the spring is, the greater that restoring force on the spring will be. And that's the same thing with the ball being struck with this bat. If the ball is deformed more, then the force is going to be greater. And this is a bat. There we go. And I need some indication that the bat is being swung. So maybe I should put some like swoosh marks, the old classic swoosh marks. There we go. Let's not over-engineer it. I do want to draw a stick person holding the bat. No, I don't. It looks rubbish. Right. So there's a duration of the collision. So let's draw a graph of what it might look like as the ball collides. So we've got our y-axis like this. We've got our x-axis like this. On the y-axis, we can write down force, and this is the force on the ball. On the x-axis, we can write time. And so that's not duration, that's time. It's a coordinate along the temporal axis. And you might get something that looks a bit like this. And just as we had last time, the area between the line and the x-axis, that area will be equal to the impulse, which is the change in momentum. The final momentum subtracts the initial momentum. Okay. I don't know if this topic's going to take tremendously long time to do, actually, because there's not that much in it, as far as I can see. We can link this to the previous broader topic of dynamics, where we were talking about vehicle safety, and we talked about how crumple zones increase the duration of collision, reducing the acceleration that the human body will experience. But of course, acceleration isn't the important thing. Force is the important thing. Surely it's forces that cause ligaments and internal tissues to snap. So it is, we could say F equals ma and say, there we are, that's why acceleration is proportional to force. But we could do it all in terms of impulse as well. We can say that we want to, for a given impulse, increase the duration of the collision so the impulse rate is lower. And that means the resultant force on the body parts will be lower. We can do that. We can completely talk about mass times the change in velocity. So that's mass times the final velocity minus the initial velocity. We can totally do this in terms of impulse. All those vehicle safety talks that we had. We can use this to measure the change in momentum of a body. If we measure the force of an impact versus time. So we can have sensors that detect force by how much they are deformed. It's a simple sort of sensor. I don't really want to draw a sketch. Well, I suppose I could draw a sketch of it. Let's imagine a ball is like this and it's coming in, and we've got some sort of sensor here, which is connected to a computer. So this is, we're talking about data logging here. This is connected to some sort of computer. Look at that computer. That is a computer right there. I'll call that computer. I'll just call it data logger. That's what we're talking about. Now, in this case, what happens is the sensor is deformed during the collision, and the data logger can measure that deformation and interpret it as a force because of Hooke's law, which we did at GCSE level. So data logger detects, well, it doesn't detect, it interprets. So data logger interprets that as force, and it records that over time to produce above graph. So we can use data loggers and use sensors to determine the impulse. So we could say impulse of ball in collision can be determined. I don't want to say measured because it's not a direct measurement. Determined might be the closest we can get to a direct measurement, though. So there's our ball. There's our U. As the ball comes in, strikes the sensor, and of course the sensor becomes deformed. We can use that to work out what the final velocity, or we can use that to work out what the change in momentum of the ball is, and therefore the change in velocity of the ball. We can do all this sort of thing. Now, what's interesting is that all of the forces of these impacts are always 90 degrees to the surface. So if I got my ball and I had it coming in at an angle like this, then I would detect, and the same initial velocity, I would detect less impact force than if the ball was coming perpendicular to the surface. Its velocity was perpendicular to the surface. I mean, that might sound obvious, but it's worth stating that impact forces, or we could call them contact forces, are always normal to the tangents at the point of contact. between two bodies. Now, what do I mean by this? Well, let's take the simplest example, which is a round object striking a flat surface between two bodies, plural. So let's consider a round object. I'm going to get my drawing tools out. So let's consider a round object colliding with a flat surface. So this is maybe, if you're into sports, a cricket bat, because that has a flattened surface, doesn't it? Just like that. And if we say that the initial velocity of the ball is in this direction, like that, then there's no component parallel to that surface of the initial velocity. The force, and I've just figured out a little hack to make sure the line is perfectly horizontal, is to use the rectangle tool. How about that? That's cool. The force on the ball will be equal to that. So you can see that it is normal to the surface, 90 degrees to the surface. If I drew a tangent, which for a flat line with the surfaces doesn't make much sense, but for the circular ball, the spherical ball, it does. If I drew a tangent, it would be, F would be 90 degrees to the tangent of the ball's surface, the ball's perimeter at that point of contact. So maybe I should draw a little 90 degrees symbol in here so that we are clear that is 90 degrees. So contact force on ball, normal to surface. Okay, fine. So if the surface was at an angle, let's say the surface is, let's do another one. Let's say the surface is at an angle like this, and our ball is falling and it collides with the surface like this. Even though the ball's initial velocity is, let's say, vertical, this is the direction of the initial velocity of the ball, that doesn't matter if that is what U is. The force will be 90 degrees to that surface. The force on the ball will be in that direction. Just like that. So the ball is falling on an angular surface. It's going to have a change in velocity, which is in a direction not parallel to the initial velocity, which means we can resolve that change in velocity into two components: the component parallel with U and the component perpendicular to U. Okay, F is going to be, and we can see this from the, oops, scroll too far, we can see this from the equations up here, that F is going to be parallel to V minus U, the change in velocity. Just like that, because t is a scalar, the duration is a scalar, and m is a scalar. So F times t is equal to mv minus u. Let's write this in black as F times t divided by m is equal to v minus u, just like that. But this has to be a vector difference. Vector difference, just like a vector sum. And that's important. So we're going to probably have some component of velocity up there and some component of velocity in there after the collision, sort of Vx and a Vy. We have initially got a Uy and Ux is equal to 0. Just like that. Okay, And we can resolve the vectors. If we know the angle here, we can resolve those vectors to work out what's going on. So that's a simple case of resolving vectors. I say simple, it's not that simple. It takes a bit of thought and a good diagram, but it is just resolving vectors to work out what happens. We can actually do this by resolving forces first, if that's easier. Can resolve perpendicular, that's the symbol for perpendicular, components of force first, if easier. And so we can say, right, what's the vertical change in velocity? What's the horizontal change in velocity? And then use Pythagoras and other trig to get the magnitude and direction later. We can do that if it's easier. Right. The last thing we're going to talk about is spherical objects, or let's just say circular. Keep it in 2 dimensions. Circular objects colliding. So if we have circular objects colliding, let's take that one and then let's duplicate it. Let's imagine 2 objects colliding. Boom, 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 like this. Then there is going to be a tangent, and I'm going to do a terrible job of, yeah, not great. I'll move this. If you've got a ruler, you'll find it easier. Let's move that to there. There we go. That's the tangent. We've got a tangent. And this is the tangent regardless of the initial velocity of the balls. So if this is, let's say, ball 1 and this is ball 2, we can have perhaps u1 in this direction. And maybe we can have u2 in a different direction. Maybe u2 can be in this direction. Let's get a straight line tool out. It really doesn't matter what the initial direction of those velocities are. When they collide, the forces are going to be in the directions shown, regardless of their initial velocities. So force, this one's going to feel a force in this direction. This one's going to feel a force in this direction, just like that. So that force is the force on object 1. That force is the force on object 2. And then we can see that object 2 is easy because that force is going to be equal to a rate of change of momentum. So if we say that's equal to, say, m over the duration of the contact, v minus u, that's v2 minus u2, assuming they've all got the same mass, so I only have to have one m, and we can work out the change in velocity. And that's all one-dimensional, that's fine. Now, in the case of object 1, it's the same equation, but we have to resolve the vectors. So this is going to be v1 minus u1, and u1 is there. We know what f1, m, and t are, then we can calculate what v1 will have to be. So v1 would be equal to, let's work this out, so f1t over m add u1. It would be equal to that. And we can do that vectorially. So we can put in our ijk notation and add up those terms, which we did quite a while ago now. We can do that if we wanted to. Or we can resolve the force, and we can handle a component of force that's parallel to u and work out what v1 is. In that direction, we can work out a component of force that's perpendicular to u, and so on and so on. The perpendicular component, that's going to be equal to 0, so that would be, again, quite straightforward to calculate. And I'm still hinting at Newton's third law. It's so tantalizing, isn't it? Look, F1, the magnitude of F1 will equal the magnitude of F2 because of Newton's third law. And I haven't even said what it is yet. It's also because of conservation of momentum. Conservation of momentum is a consequence of Newton's third law, or perhaps Newton's third law is a consequence of conservation of momentum. Right, that's all I'll say there. What I will say is that if our object is colliding with a surface and rebounds, then there's a bigger change in momentum than if the body collides with the surface and stops. So let's look at those two situations. Collide and rebound versus collide and stop. Well, if we collide and rebound, we've got before and after. We've got our velocity before and our velocity after. And let's copy this circle so it's exactly the same. Velocity before and velocity afterwards. And yet if it collides and stops, then we have our velocity before and then 0 afterwards. I'm going to label all this. Right, so let's label all this. Let's go before, let's get the pen out. So before, after, and I'm not interested in what it's colliding with. Before, after. Again, I'm not interested in what it's colliding with. Let's say that we have a velocity this way and then a velocity this way. Let's have the same velocity this way and then v is equal to 0. So what's the change in momentum going to be? Well, the change in momentum is going to be equal to the mass multiplied by v minus u. And if we say, for simplicity, that u is equal to v in magnitude, that's what the notation means, and the arrows are in opposite directions, then that's equal to m multiplied by 2 lots of u. So 2mu. I should have a minus in there, of course, because we are slowing down and going back where we came from. So minus 2mu. That's the change in momentum. Whereas in this situation, change in momentum is still equal to m multiplied by v minus u, but v is 0. So because v is 0, then change in momentum is equal to minus mu. And can you see that it's half as much? Now, the only way to have the final velocity equal to the initial velocity is if we don't lose any kinetic energy. So if we don't lose any kinetic energy in our collision, then we end up with twice the change in momentum than if the object stops when it collides. If the object stops when it collides, half as much change in momentum. Okay, fine. So what? Well, so if the duration of the collision is the same in both of these cases, then the colliding and rebounding will have twice the impact force than colliding and stopping. So I need to somehow get that into my notes. I could say that collision force is going to be equal to minus 2mu divided by t, whereas in this case, the collision force is only equal to minus mu divided by t. So you can see it is lower if the objects stop. And that's why our crumple zones are designed so that we don't bounce back. We don't want to bounce back. We want to stop dead. So minus 1, minus 2. So the idea of putting springs on the front of all of the cars, so when they collide, they all bounce off each other and the cars don't get damaged, would actually mean the passengers would feel twice the impact forces which would be very dangerous. Right. Are we at the end of this topic? Yes, we're at the end of this topic, which means that the next lesson is conservation of momentum, and we're finally going to learn what Newton's third law is. And I hope you'll join me for that.